Hello everyone, welcome to our prosthetic design workshop. My name is Paul, and I'm an engineer here at Prosthetic Design. In this workshop, I will cover the entire fabrication process for a 3D printed final socket, starting from a cast all the way to a finished definitive leg. Now you might think there is no way you can make a socket in 30 minutes. And you would be partially right. The socket in total will take about 2 hours to make. But the work that I put in is only about 25 minutes. The PDI Squirt Shape 3D printer is a unique machine that makes this fabrication process possible. The Squirt Shape 3D printer is a 3D printer that uses pellet extrusion printing to make lower limb prosthetic sockets. This plastic is in a granular form, rather than on a spool in filament form. With the plastic as pellets, this lets the throughput of the printer increase, so the prints are structurally tough, and the print time can be reduced significantly. This socket manufacturing process can be broken down into 4 steps. First, modeling the socket in a CAD software. Today I'll be using Tracer, but a few other common industry softwares include Omega, CanFit, or Rodin 4D, with plenty of others that work as well. I want to mention that you can use non-O&P specific software to model the socket. I'm going to use O&P specific software in my example, but I wanted to ensure those familiar with other software programs that there are other options that work. The second step is to print the socket. This step is pretty straightforward, as we will print the socket using the Squirt Shape 3D printer. Third is to post-process the printed socket. Things like clean up the trim line or any other modifications that need to finish up the socket. The fourth and final step is to assemble the leg. This works just like any other definitive leg you might make for a regular patient, using a laminated socket or thermoformed. And that's it, so let's start knocking these steps out. To start the CAD modeling for the socket, I first need a reference, so I have something to base the model off of. Whether I get a scan of a limb, a traditional cast, or measurements to build a model, having this information will let me model the socket specifically for each patient. Today I will use a cast of a transtibial patient and a physical digitizer to make my reference model. The digitizer works by using a mechanical arm to take measurements of the cast. The mechanical arm slowly rises as the cast rotates to capture the reference model for the patient limb. So then I take the saved reference model and import it into Tracer. This is where I will make all of my modifications to the model. Now let me pause before we jump into the modifications, because there is some relevant information about the Squirt Shape printer that will affect how I model the socket. The printer works by spiraling layers of plastic on top of one another, building up the socket. If the layers stack right on top of each other, then the full width of the layer will make contact with the previously printed layer, forming a strong bond. Now if the layers are offset from each other, the layers printing might not make contact with the previous layer, or will only contact a little, resulting in a weaker bond. So this needs to be addressed when modeling so that the layers will have a good amount of contact when printing. The second consideration I will make is in the model's distal alignment. I know that's oddly specific, but the printer works around a rotational axis, which is at the base or distal end of every socket. This axis is fixed in the printer, so the center of rotation is always in the same place. I just need to make sure when modeling that the distal end of my model is aligned with the center of rotation so the socket will print correctly. The final consideration is also related to the alignment. The 0 degree mark on the rotational axis plate corresponds to the anterior alignment in the slicing software. So unless you are rotating the socket on purpose, the anterior of the model will be the anterior of the socket. Okay, now that I've mentioned these considerations that need to be made when modeling, I will walk through some of the modifications we make in-house for patients. And when I make a modification that relates to the printer, I will let you know, hopefully clarifying any confusion. First thing I'm going to do is add some landmarks, so I will have a few reference points when doing the rest of the model. Since this is a transtibial socket, I add a few points for the trim line and one for the distal tibia. I also smooth out the surface of the model so that when it is printed, the shape transitions smoothly. Now I'm going to mess with the alignment, keeping in mind that the distal end of the model is where the socket will be printed. I rotate the model so the anterior of the model matches the anterior of the software, so the model will be correctly rotated on the printer. Then I tilt and shift the model until I'm happy with the alignment. Once I think the alignment is close, I now trim the distal end of the model, as the cups that all sockets are printed onto have a slight void in them after any lock or plate is inserted, and this allows the limb to fall all the way into the socket, matching the profile of the lock or adapter plate. You can see now that I use the cylindrical adapter to check that I like the alignment of the socket. I use the cylindrical adapter to make sure the model is aligned with the fixed rotational axis, as the adapter is always centered to the printer, as long as I don't move the adapter and only move the socket. Next, I add the trim lines for the socket. I load in a preset trim line and then drag and draw the trim line until I have reached the desired shape. The landmarks I made earlier help with the positioning and height of the trim lines. I add a shelf to the posterior side of the model now to create reliefs for the hamstrings and to elongate the medial and lateral condyle surfaces. I then finish up the trim lines by making it more pronounced so it is easier to post-process. I notice that the trim line is a decent height lower than the height of the model, so I use the cutting tool to trim the model down. No need to print more material than is needed. I add the cylindrical adapter at 74 millimeters, as this will be the base and start of my print. The adapter assures that the model is aligned properly, and that the bottom layers of the model will also match up to the distal cup that starts the print. Since this model covers the alignment consideration well, I want to circle back and just touch on the spiraling layers consideration, since this model didn't need to make any of those considerations. So take this large transfemoral socket, for example. The distal end of the model has a sharp transition after I've added the cylindrical adapter. So I need to smooth out the transition to keep the layers stacking well enough. I keep repeating this process until the curvature is not too sharp. Now that we have covered how to model the socket and the considerations that come with using the Squirt Shape 3D printer, I need to convert the model into a file that the printer can understand. So I'm going to save and export my socket model as an AOP file, and then transfer it into the slicing program that comes with the printer, Limb Revolution. Once inside Limb Revolution, I will just go to the export button and press it. Then my file is saved as a TAP file, and this is what the printer can read. Now let's jump to the printer. Calibrating the printer is the first step we take to setting up the printer after turning it on. The purpose of calibrating the printer is to make sure that the measurements of the model I create on the computer match the measurements of what the printer prints. To check this, we print a little cylinder that has a computer model measurement of 79mm internal diameter. So the printed version should have this measurement as well. I need to reference home all the axes so the printer knows where the nozzle is located. On the computer, there is a button called Ref All Home, and this zeroes out all the axes to their reference values. The A axis should be 0, but the X and Z axes can be other numbers. We'll correct those in a minute. After referencing all home, I move the nozzle into position about where the first layer should print. On standard distal cups and the reusable calibration cup, this height is at 41mm along the Z-axis. I hop on the computer and type in 41mm to the Z-axis placement. So this sets the position close to the correct value. Next, I use the X-axis alignment plate to zero the X-axis, as I would before any print, by sliding the plate between the nozzle and cup so that it touches both but freely moves. The other portion of the calibration, other than achieving the correct Z-axis height, is to make sure that the wall thickness is appropriate. We like our wall thickness to be around 6mm. We recommend that when using the printer for sockets, to never go below 5mm. The wall thickness can be controlled during the print using the feed rate and spindle speed tools on the computer. The feed rate tool determines how fast the printer moves, and the faster the motion, the thinner the wall, and the slower the motion, the thicker the wall. The opposite is true for the spindle speed. As the higher the value, the more plastic that is extruded, and the lower the value, the smaller the amount of plastic that is extruded. Using a combination of these values allows for altering the wall thickness to the desired width. After the calibration cylinder is printed, I take a wall thickness measurement and an internal diameter measurement that should match the modeled value of 79mm. The internal diameter is very close at 78.93mm. I had a good guess apparently when pre-positioning the Z-axis. I can go onto the printer's computer and change the value of the Z-axis position to account for this small deviation. The wall thickness is good, so I do not need to alter the feed rate or spindle speeds. Now that I have made sure the printer is calibrated, I can move to the setup procedures that are done for every print. First, I check to make sure there are enough pellets in the hopper to complete any print. If the hopper is full, it will print any socket that will fit in the printer, which can get pretty big. Second, I'm going to attach the distal cup to the printer. The important thing to consider when attaching the cup is the orientation. Since 0 degrees is the reference mark for the anterior of the socket, the orientation of the cup may be important for a lock push button or lanyard slot on the finished socket, depending on the type of suspension being used. Since this socket is getting an elevated vacuum shuttle lock combo, I will be using a standard height cup with a hole in the side for the push button. The orientation of the push button matters, as I would like it to end up on the medial side of the socket. This patient is a right side transtibial amputee, so if the anterior is at the 0 degree mark, the medial side is at the 270 degree mark. We have pre-marked the medial sides with an R and an L for right and left, respectively. This helps when you don't want to think too hard about it. The third step is to zero the x-axis. So I take the x-axis zeroing plate and place it against the top of the mounted cup. I then move the nozzle to a point above the cup and plate where I can slide the plate up and hit the bottom of the nozzle. The nozzle is then slowly moved away from the cup until the plate is able to slide between the cup and nozzle, touching both. I jump over to the computer real quick and set the x-axis position to 0. Fourth, the nozzle can be moved up the z-axis to a position of about 100 millimeters, as this is the starting position in all G-code files. And lastly, the lip of the cup needs to be heated. This ensures a better bond between the cup and the printed plastic. To heat the cup, I use a small butane torch and continuously rotate the cup until the surface appears glossy. That completes all the setup. So now we go back to the computer, hit the start button. Once I have started a print, I like to watch the first few layers just to make sure everything is going well. I watch to make sure the infill groove is full and that the second layer makes good contact with the cup. Now that I am content that things are going as expected, I will let the printer do its thing and be back in about an hour and a half. And we're back. The socket is all done, and to pop it off the printer, I just remove the 2 holding screws inside the cup and pull it off. Now we are ready to post-process. Some of these steps will be familiar to those that cut and grind thermoformed plastic sockets, or even thermoformed orthotics, but I just want to show you that a 3D printed socket doesn't need special treatment to clean up when taken off the printer. In this example, we want to use vacuum, so I will be heating the socket to smooth the proximal end before I grind the trim lines away. To smooth the socket, I rotate it slowly, as I hold the butane torch close to the surface, being careful not to remain stationary, as I want to avoid burning parts of the socket, discoloring the surface. The discoloration comes from the smoke particles adhering to the heated surface of the socket. I know I have smoothed the socket to the finish I am looking for when I can see the force of the butane torch starting to push the surface around like a liquid. Once the entire area I'm trying to heat is smoothed, I will then let the surface cool. before I grind the socket. I use an air-powered angle die grinder to cut all the trim lines. A normal cast saw works too, but the die grinder is just faster. With the excess material removed, I now shape the trim lines with grinding cones of differing roughness grits to shape and smooth the socket. The cones start coarse, making their way to a fine grit, and then finishing with some felt cones for a final smoothing. The socket is now finished. Just need to combine it with the other components for the leg, and it's ready for patient use. This will be similar to any prosthetic leg you may have built before. Nothing truly new, other than it's being built with a 3D printed socket. I mentioned earlier that we want to use vacuum for this patient. So I will be using a PDI EVLS shuttle lock. The lock has a top sealing O-ring for vacuum, and the pin gives a secondary form of suspension. I insert the lock by removing the push button and then sliding the body of the lock into the cup, aligning the 4-hole pattern on the lock with the 4-hole pattern on the cup. Next, I attach the Limb Logic pump and a sliding pyramid adapter to the socket using 60mm bolts. To the sliding pyramid, I will attach a pylon with a pyramid receiver built in. We are going to use the LP Very Flex foot, as this is a low profile, everyday foot for this patient. Then I will attach a pylon adapter to the pyramid on the foot, and then combine the two by setting the clamping screws. The leg is now finished, ready to sleeve and then give it to the patient.